Welcome back. In the previous video, we talked about the meshing operations and how we can do mesh for external and internal flows. In this video, we will start the most important part of these tutorials and we will continue with the Fluent component. Once again, we have an external flow made out of component systems and an internal flow made for analysis systems. Again, as it was with the mesh, there is no reason why we set up external flow like this and internal flow like this. I just wanted to show you how to do simulation with both component systems and analysis systems. Let's quickly go over the geometry and mesh and start talking about the Fluent component. Let's look at the geometry. So this is our geometry. Once again, we had this sketch. We moved it to the center. We generate this enclosure around it to mimic a wind tunnel. We make sure that the walls, the upper and bottom parts of it, is defined away from our body so that the boundary layer that will form in these walls do not affect the flow region around this airfoil. And we leave a large space in the back to study the airflow in the back of this body. And we generate this Boolean operation to subtract the airfoil from the fluid region to be just left with the fluid region, and we define it as fluid. Let's look at the mesh. So this is the mesh. It's a very simple one. We make the mesh and define inlet, outlets, and walls, as well as our body. We went over the mesh in the previous video, so we're not going to talk about it now. And let's start with the setup, the Fluent module of external flow. So in Ansys Fluent, when we run setup, the solution will also come with it. In Ansys CFX, it's a bit different. So when we first launch the Fluent launcher, we are welcomed with this window. So first, the solver options. The double precision, it's basically 64 bits. If you have a good system, it's okay to check this. And the parallel local machine, this solver processes. This basically means how many CPU cores will be used during the solution. So for faster simulations, in order to calculate it quickly, you can use the amount of cores one less than the maximum amount of CPU cores in your CPU. You leave one core to Windows or other operations. For example, if you have a CPU with 6 cores, you can use 5 here. If you have a CPU with 12 cores, for example, you can use 10 or 11. And how are you going to know that? You can check how many CPU cores you have by going into the task manager. And when we launch Ansys Fluent, if we are seeing certain errors, for example, it's not loading or you get this weird error, try reducing the number of CPU cores here and see if that works for you, because if it exceeds that value, you will get an error. It might say different things. It might say licensing error, it might say launcher error, and that this is a one solution. After doing all the settings, we can launch it by clicking start here. So this is the UI of Ansys Fluent, and let's start by talking about this task page here. So the velocity formulation, the important part here is solver. We have the type of solver and the velocity formulation, and we have here time. So these are pretty self-explanatory, but the time here, the steady and transient, what it means is in the steady flow, the solver assumes the flow does not change over time. So it finds a final solution where things like velocity, pressure, and temperature stay constant. And it's faster, it uses less memory, and it's good for simple flows or fully developed flow in a pipe, for example, or external aerodynamics at constant speeds. And the transient solver here, it simulates how the flow changes over time. It solves the equations at each time step and updates the solution. So using transient solution, you can see how the flow varies over time, but it is going to take much more memory. It's going to take much more time, and it's basically good for unsteady flow and a bit more advanced aerodynamic studies or flow studies. And this turns on the gravity. As I said, these things, it's the same with transient. It makes the simulation take more time. So we are going to keep things simple. And let's talk about the ones here. So starting from general, we talked about this part and the models. So we are going to talk about two things here, the energy and the viscous model. We are going to talk about energy in the internal flow, so let's talk about the viscous model. So the most important thing here, and we can right click and hit edit. When you are doing your simulations, whether you are doing it for a project, whether you are doing it for another reason, whatever, one of the most important things is to select the correct viscosity model. And how can we select the correct viscosity model? Most of the time in your simulations, you have two models here, K-Epsilon and K-Omega, and we have something else called SST K-Omega, as it is selected right here. It's in the SST model. These three models will be enough. And also, in addition, you have laminar flow here, which is if you are absolutely sure that your flow is laminar. And we have the K-Omega flow, K-Epsilon, and K-Omega standard. So how are we going to select which one to do? Let's start with K-Omega standard model. But before we start, let's talk about what we are doing here. What is the solution type? What do we mean when we say solving? So Ansys use something, these equations that you see here, they are called RANS equations, and it stands for Reynolds averaged Navier-Stokes equations. So in these equations we will have four common parameters. It will be the x velocity, y velocity, z velocity, the continuity function, and the other two equations. And these equations that you see here, K-Omega and K-Epsilon, or the SST K-Omega version here, are those two additional equations, or not the additional equations, but how the Navier-Stokes equations are Reynolds averaged, basically. And for example, for K-Omega turbulence model, this is from Wikipedia. It's a very simple explanation. We are not going to go into too much detail, but the important part here, the thing that I want to show you, is this part, while the evolution of K and Omega is modeled as, and these are the two equations. So when we complete this and we are solving this, you will see two additional equations in the solver that's called K and Omega. And you know the Navier-Stokes equations, and these are the additional equations that basically, not these exact equations, but basically what is going on behind the screens. Similarly, this is for K-Epsilon, and you can see here for turbulence kinetic energy we have this, and for the dissipation epsilon we have this. So from here, let's talk about this. We're talking about dissipation, we're talking about standard KE or K-Omega, and this is basically how we are going to select our turbulence model. If we are dealing with high boundary layer formation, if we want to model the boundary layer as precisely as possible, for example, maybe we are dealing with internal flow, and as you know, for example, think about a pipe, and in this pipe we have the normal flow region, and due to boundary layer formation our flow is getting slower and slower, and at some point we obtain fully developed boundary layer. So for example, if we want to study the flow in this region, in the fully developed boundary layer region, we need a very precise modeling of this boundary layer. Then we are going to use the standard K-Omega equations. Why? Because K-Omega turbulence model accurately models turbulence without needing wall functions. So it's able to capture low Reynolds number effects very well. However, K-Epsilon model relies on wall functions, and therefore it struggles to accurately resolve the viscous sublayer near walls at low Reynolds numbers. However, K-Epsilon model is very good at modeling high velocity flow away from the surface. So for example, in your simulation you have high velocity and your main focus is how flow behaves around and away from the solid object that you're modeling, then K-Epsilon model should be your choice. So then what is SST K-Omega? This is from CFD Online. I will also put the link in the description so you can go and read this for yourself. But the K-Omega turbulence model, SST K-Omega turbulence model, combines the K-Epsilon and K-Omega, where in the close to wall regions it applies the K-Omega model, and away from the wall it applies the K-Epsilon model. It doesn't do either of them as good as these models, but it's basically the safe spot. And in a vast majority of your simulations, whether you're doing internal or external flow, you can use SST K-Omega. So I said that we are using RANS modeling. The RANS modeling, we said that it stands for Reynolds averaged Navier-Stokes equations, and we said that this 2 and the SST K-Omega and the other models are part of that. And what is these two then? The large eddy simulation and detached eddy simulation. Well, these two do not fall into RANS category, but the large eddy simulation, for example, directly resolves large turbulent eddies and models only the smallest scales. So it's a bit of a different one. It requires a much finer mesh, more time dependent. It's a bit more different. I'm not going to say complex, but it's different. And the same exact thing goes for the detached eddy simulation and the scale adaptive simulation. These are called hybrid methods that use RANS modeling and less modeling. So it's a bit different, but the important thing here is to select the correct viscous model. And the correct viscous model, most of the time, you can use SST K-Omega and K-Epsilon and laminar flow if you are absolutely sure that your flow is laminar. And these explanations that I just told you, standard K-Omega near boundary layer, K-Epsilon away from the body, and SST K-Omega as a bit of both, this is a good explanation. You can use this in your homeworks, you can use this in your assignments, and these are acceptable explanations. So we will select the SST K-Omega function here, and we will continue. Let's look at the materials. So this is where we define our materials. We will define the fluid as air. By the way, when you first launch Fluent, you will have your mesh here. And everything that you defined, for example, we defined this part as inlet and this part as outlet and these parts as the walls. We cannot see the body inside it, but it's also there. If you do not see this part, if your mesh doesn't appear here, or there's a problem, maybe it is this part is also defined as the wall, you don't have an inlet, then you can immediately close this, go back and fix your geometry or your mesh. So let's imagine we want to change the air. We will change this fluid for the internal flow, but we do it through this window, or we can change the properties here. The same goes for solid. Right now, every solid thing that is inside this simulation is defined as an aluminum. Let's let it remain this way. Let's talk about the boundary conditions. So this is where we define the boundaries of our model. So we will start from the top, the body. As you can see here, I told you that if you name your airfoil as body or solid or whatever, you are going to see this here. When we double click this, immediately we can access that. And the type here, this is the important part, we will define this as wall. So right now it is going to act as a solid object, and we can set different things here. We are going to let it be stationary, no slip wall, and so on. And the inlet. So after selecting this, we can select edit. And here we will be able to define our velocity. And let's define our velocity, for example, as 100 meters per second or 75 meters per second. We're not going to change the inlet gauge pressure or other values. When you, as I said previously, if you advance in this field, if you learn more things in this field, you will be able to study these more closely, but this is a tutorial for beginners, so we are going to skip all this, and we will hit apply, and we will close. And the interior fluid region, this will be defined as the interior region. Pretty simple. This is the fluid inside the wind tunnel that we mimicked here. And the outlet, the pressure outlet. So there are different outlet types. We can define it as outflow. We can define it as mass flow outlet. We are going to define it as pressure outlet because it's simple, and we are going to select gauge pressure as 0, and we are going to keep everything as it's same. And the wall, this is the walls that we defined here. We are going to define the walls as the wall. As I said once again, because we named these walls as walls, we are able to see them, and we are able to access them through this task page here. Another thing is the reference values. We are going to talk about reference values in a bit, and let's move on to the solution part for now. And in the solution, the first one is the method. We're not going to make any changes here, just going to skip this part as well. You can keep everything the same here, and the control part again the same thing, and report definitions, we will talk about this in a bit now. And the monitors, let's come to this part. This is important. So in here we see the residuals. when we right click and edit, we see these values. So what are these? First of all, we see our residuals: continuity, x velocity, y velocity, z velocity, k equation, and omega equation. And we will monitor all of these, and we will check for convergence for every single one. And this one is the criteria. You can think of this as the error criteria. So what does this mean? In a bit, we will initialize this project. And when we initialize this project, the Ansys is going to define certain numbers based on our inputs into the system along this object. And during the calculation process, it is going to make calculations for every single residual that you see here. And the end value that is obtained after each iteration of calculation will be compared to the initialized value, and the error value will be found. And when the error value falls below this absolute criteria that you enter here, that specific residual will be accepted as converged. And when every single residual that you see here is converged, then the entire solution will converge and your solution will come to an end. So what numbers should you enter here? Well, it's actually very simple. This is 1 times 10 to the power of minus 3. And if you think it from yourself, you can make calculations to this point by hand. So this is a very high number, and we can reduce this number. And in the CFD studies, you would see that most of the time, this number is taken as the power of 6. But for this part, we are going to not make any change on this part to achieve faster results. So we are going to keep it as this. So let's talk about the reference values and the other things here, the more important part. So I told you about the convergence situation, but there is a very important question here. If you study CFD and if you go further into this field, at some point you will probably come up with this question, and I am going to give you an answer right now, and the question as well. So the question here is, if your solution is converged, but you used wrong viscosity model, then is your solution acceptable? Is your solution necessarily have to be correct? And the answer to this is no. And the simplest way to explain this is, think about a very simple mathematical equation. X to the power of 2 is equal to 9. So what is x? And immediately you might say x is 3, which would be correct. But not necessarily, because x could have been minus 3 as well. And because the 3 that you have entered into that x value provided the answer, you think that this is correct. But in reality, the correct answer was minus 3. And minus 3 and 3 are completely different numbers. So your solution is actually incorrect and your result is unacceptable. So there are ways to make sure that you get answers that are closer to being accepted as correct. And the best way to do this is add additional parameters. For example, you can make that same equation, but you can add different parameters into that equation. For example, you can bring absolute values into the equation. Different things. And one thing that we can do here is to define additional convergence conditions. And we are going to see how to do that now. First of all, we are going to go back to reference values here. What we are going to do here is we are going to make Ansys calculate drag coefficient as well, which is, by the way, also if you want to calculate drag coefficient using Ansys Fluent, this is the way to do it. And we are going to calculate drag coefficient, and we are going to add that drag coefficient into this equation as a convergence condition. So in the reference values, we are going to compute from inlet, and the area is asked here. So what is this area? This area is the frontal area of your geometry. For me, this is around 0.8, and the density is basically, this is the air values, and the pressure is, let's enter this as 100, and the temperature as 300, and the reference zone will be the fluid region. So these are the reference values, and when Ansys is calculating the drag coefficient, it is going to look at these numbers and it is going to calculate it based on these numbers. So for example, you are calculating your drag coefficient and you are getting a very high number, It isn't supposed to be that way, and you are sure your geometry is correct, you are sure your mesh is correct, then one possible answer is that you probably entered this area value incorrectly. We will continue with the report definitions. So we will click this and we will right click and we will select new. And as you can see here, we can add multiple different report definitions. We can calculate lift, force, moment. We can calculate flux reports. We can have volume report. We can calculate, for example, volume average, so on. And we will look at the drag. Here we select drag coefficient and drag force. So this one is the name, and we will name this as drag 1. And this is the force vector, and this basically defines what your force will be, and you can choose this based on this coordinate system here. So it's in the x direction. We will change this to z direction in this way, and we are going to select the zone. So as I said, once again, the named selection appears here, and we can select it. The walls basically is the outer walls. All the solid regions are shown here. We are going to select the body because we want to know the drag coefficient for our body, and we can also calculate drag force through here, by the way. And we are going to print to console, so we will be able to see the drag coefficient in the console here as well, and we will select OK. So now we told Ansys to calculate the drag coefficient as well, but we did not add it as convergence condition right now. So to do that, we will select this convergence condition, we will right click and we will select edit, and we will add one here and report convergence. The report definition, as you can see, it appears here, and we will not change this one, but these two values, ignore iterations before and use iterations. So we will select here as 20 and here again as 20. So what are these two values? This means that the first 20 iterations will be ignored. Why? You will see during the calculation as well. In the first 20 iteration, our drag value will jump up and down because it's the first few calculations and they need to be ignored. And after a while, it will settle down and we will use after the 20 iterations. And we will choose condition as all conditions are met, and we will select OK. And then we will go to initialization. We will use the hybrid initialization and we will select initialize. So here, as you can see, we get this warning, convergence tolerance is not reached. So this is because probably our mesh quality is a bit low. We did not spend enough time to perfect our mesh. It's okay. We can increase the number of iterations here. To do that, we can select more settings and increase the number of iterations. So after 25 iterations, it's done. So this does not necessarily mean our solution will be incorrect. This is a good way to check this, because if you are not able to reach this convergence tolerance, and more importantly, if it is going divergent, for example, after 50 iterations, it's starting to go up again, and it's starting to diverge, it means your mesh is certainly poorly made, and you need to increase the quality of your mesh. You need to recheck that, or maybe you have something wrong with your geometry. And then we will come to the run calculation finally. The number of iterations here. Do not enter a low number here, like 100, because here is the thing. When you reach convergence, even if you enter a value like 10,000 here, when you reach convergence, let's say at the 100th iteration, it will stop. So do not fear to enter a big number here. Let's go with 1000 iterations, for example, and we will not change any of these. And then finally, we will select calculate. First few iterations here are changing. So the up to 20th iteration here, it's not acceptable. But after a certain period of time, it calms down. And the scaled residuals, as we can see here, the x velocity, y velocity, z velocity, k and omega value, As you can see, every single one is calculated here. And right now, for example, after the 51st iteration, we get this message. The drag value has converged. So our drag value is at a point, and we finally get this text that says solution is converged. And as I said, for example, we enter here number of iterations as 1000, but the solution is converged at the 68th iteration and the solution is over. So do not enter a value here, for example, like 50, because your solution is going to converge 80 iterations later anyway, for this case only. So this is basically how the solution is done. So now let's look at the internal flow. Let's pretty quickly investigate the geometry here as well. We have a simple pipe, straight long pipe. As you can see here, just a long pipe. We extruded this here with this sketch, and we made sure that it is defined as fluid here in the fluid solid, because when we extrude this initially it is defined as solid, so we made sure to change this to fluid. And in the mesh part, we made sure to define inflation mesh in the outer boundaries to study the boundary layer better. As you can see, the boundary layer in the outside and the normal mesh here. And in the named selections here, we don't have an internal object, so the inlet, walls, and the outlet is defined as this. Once again, when we launch the setup part, we are welcomed with this window. Once again, through this mesh window, we check our geometry and we make sure that this part is inlet, the walls, and the outlet. So we talked about these and the general and the model parts in the previous video. Let's change this to standard K-Omega, because this is an internal flow. And for the materials here, let's change this to water. So how are we going to change this to water? We can add water from Fluent database directly, or we can define a additional fluid, because if you have a type of material that is not inside Fluent's database but you know its properties, you can use this user-defined database. But we will use the Fluent database here. And for water, when we go to the bottom of this list, we have water as liquid here, water liquid, and we will just select this, hit copy and close. And here you can see water liquid. Under the cell zone conditions here, we have water as our fluid, but the material name here is what's important. We will change this from air to water liquid, and then we will select apply, and then we will close. After doing this, we can actually delete the air here to be sure that the only fluid is water. And in the boundary conditions, once again, we have different types. We explained them in the external flow. We are just going to define a value here for inlet, and that value, let's enter 5 meters per second. And the important thing here is, in the previous one we defined the K-Omega. I said to you that we were going to talk about the energy, so let's talk about the energy here. This energy function allows us to control the heat operations in Ansys. So we are going to right click this, edit, and we are going to turn it on here. So after turning energy equation on, now we will be able to define additional parameters here. Let's go to wall here and select edit. Right now, as you can see, this thermal window is activated. And under this thermal window, we can select heat flux, temperature, or other things. Let's select heat flux. And let's say, for example, 10,000 or 100,000. So what does this do? This basically applies heat to the wall part of our geometry. Let's select apply and close. So this water, as it is flowing through this part, a heat flux is applied to it through these walls. And this is how we can set that up in Ansys Fluent. So along all this way, all these parts, a heat flux will be applied. So let's continue. We are going to skip the other parts. We already talked about them in the external flow. And let's change this residual part here. Let's add additional two zeros. And as you can see here, you can also write it as such. The energy residual is also added because we added energy equation into the calculation. Let's decrease this value because this is a much simpler simulation, and let's initialize this value. Again, it's not reached, it's okay. So after 20 iterations, it's done. So let's run the calculation. Let's leave a bit more space for the monitors. And 1000 iterations, and let's calculate. So even though this is a much simpler simulation, it took a lot more time because we entered much lesser residual convergence criteria. And as you can see through the scaled residuals, it all converges, and we get this once again message that says solution is converged. So this is basically how we do simulations. In this video we talked about the external and internal flow, and we talked about the most important part of CFD. In the next video we will talk about the result part, but I want to give this insight before we end this video. There is a term in computational fluid dynamics in CFD called colorful fluid dynamics, and it's a term that is used to define simulations and studies where arbitrary numbers are given without caring about the results, without paying attention to what is being done, and basically simulations or results that has absolutely no meaning. And this is the important part, because this software that you see here, this is basically like a calculator. It will only do calculations based on your input. It is not going to question your input. It is not going to give you an insight on this input. Imagine, for example, you're in an exam and you are asked to calculate kinetical energy, right? A simple question. You are given the mass, you are given the velocity. And what you do is you take the square of the velocity and you divide it by 2. You use your calculator to do that and you enter that value. But your value is incorrect. You didn't include mass, but your calculator will not question that. Your calculator will not tell you, hey, you didn't include mass, so your solution isn't correct. And that is the important part of CFD, because CFD, the most difficult part, the real part, is to be able to select the correct things, make sure that you enter the correct values, make sure that you put in the correct variables, and also at the end being able to make comments on your results, being able to understand if your result is correct or not, being able to come to the conclusion that the obtained result is acceptable, or what is wrong with that result. If you have a problem, is it because of your geometry? Is it because of your mesh? Is it because of your solution? Is it because you selected the wrong viscosity model, for example? And that is the important part and the real part of CFD, because after watching these tutorials with these things that you learned, you can do a vast majority of simulations, but that does not make you good at CFD. Being good at CFD means being able to understand the results, being able to make comments on it, being able to understand what is going on behind those calculations, as I explained to you here, the Rens modeling, the less modeling, these things, these equations. And that is the most important part of CFD. So if you are watching this video to complete an assignment, a project, then the things that you learned here are good enough for that. But if you want to develop yourself in the field of CFD, if you want to learn more things about this and be involved in this, your expectation should not be learning many different CFD programs, because you can learn any CFD program in a couple of weeks. It would take you 2-3 weeks at most. You can be familiar with the tools of that program. You can understand how to use them. But the real thing, the thing that you should be expecting, is understanding what is going on behind those programs. When you hit calculate, when you are making this simulation, what is happening behind the screen and what your result means. So once again, thank you for watching, and in the next video we will be talking about the result component.